what I'd like to do in my talk is to explain to you why I'm so excited, enthusiastic about using functional programming technology, describing and implementing hardware. So Simon before talked to you about why it was wonderful to use functional programming for doing software, but I think it's fantastic for doing hardware as well. And I hope to try and convince you about some of the reasons why I used languages like Haskell to build systems that create circuits that we implement on FPGAs. And I think there's a kind of a wider story to be told about this, because I think in the future the distinction between hardware and software is going to be blurred, and we're all going to have to learn to program very heterogeneous kinds of systems, which are going to present major programming challenges for us. So I put just a little cartoon here about what the future processes might look like. So maybe you should take this literally, it's just meant to motivate a heterogeneous system. So maybe future processors might have a small number of legacy cores that run things like, say, Windows, or probably some other operating systems as well. Lots of small cores that are maybe ARM-like. We've got special communication mechanisms to speak with each other. And these things might not even run operating systems, might run things which look more like language runtime. Well, on-chip network to connect these things together. We'll have things like reconfigurable data paths, which might be the evolution of today's GPUs as being more general purpose computing devices. We're already beginning to see that happen. We might have the evolution of today's FPGAs, these Lego-like bits of hardware, which I'm going to talk a bit more about. Who knows, we might have graph reduction engines or neural net engines, DSP codes. We can have just lots of different things that compute. And it's a significant challenge is going to be how to model and program these kind of things. And maybe this means that, maybe one path is that we're going to have to let lots of different languages which are tuned to all these different resources, CUDA type things for the GPU, C# type things for the software. But I kind of feel that that's not the right direction to go. I think we can do a lot of things called domain-specific languages and embedded domain-specific languages, which work by using a normal language and embedding inside it domain-specific languages capture the essence of a particular application domain. And in my presentation today, I'm going to present a domain-specific language for describing hardware for you, mainly hardware for FPGAs. That's what the bulk of my talk will be. And at the end, I'll say a few words about how you can take the same descriptions and retarget them at things like GPUs or multi-threaded software. Because there's something about these domain-specific languages which capture the essence of the problem at the right level of abstraction. The right things were said, and other irrelevant details were omitted. And the other important thing about these domain-specific languages is that they're embedded. You don't create new language. You don't get Lex and Yak and create a new parser, etc. There's an existing language that you kind of live inside and take and make benefit of. And that's what I think is going to be one of our biggest tools for being able to target these heterogeneous multi-core systems. So today I'm going to tell you about a project that we worked for many years to program these chips called FPGAs. I'm sure many of you know what FPGAs are, but for those of you who don't, FPGAs really are like Lego-like bits of hardware. They contain lots of blocks, which you can figure to be like AND gates, OR gates, registers, and there's wires that you can connect them off a wiring network, a on-chip network, which lets you glue these things as you like. So basically, I think of this as being the Lego of hardware, and you can just reprogram these chips for a cable or some other interface. You send the bits down the wire, and the thing gets reconfigured. And at the heart of these devices, there's a bit of circuitry which basically stores a truth table inside a bit of memory. So these things just have a bunch of truth tables stored in memory, connected with a wiring network. And FPGAs have a major application in areas like networking, in video, in base stations for wireless, etc. So I'm sure many of you know much more about them than I do. And here's a picture of a fairly crazy FPGA. It's quite a large one. And these things in the middle are the gates that you can reconfigure. This crazy FPGA's got 4 processors also burned onto the silicon. These are PowerPC 405s. So you can compile software to these things, you can compile hardware to these things, and hook it up however you like. So it's like a blank canvas. And normally what I do is I fly and I bring an FPGA board with me, and I do a bit of a demo and program it. But I get too much problem at airports because people ask me, what does this do? And I say, what? Anything you like, whatever you like. I discovered this is the wrong answer. And now I can saying that, well, it's a networking card, or it's a video card, or something like that. And that worked for a while, but until recently I had a beard and moustache, and looking more, so I just stopped flying it altogether. So today I can just show you the picture of the board. But if you come and visit me in Cambridge, I'll happily give you demonstrations. So I'm going to describe to you an embedded domain-specific language called Lava, which we've worked on for many years with colleagues at Chalmers. So this is just a bunch of programs we've written in Haskell. It's just a Haskell library. There's no magic. We haven't invented any new syntax, no Lex or Yark. We're just going to live inside the Haskell world and try and use some of the advantages of being in a lazy function language to describe and implement very efficient circuits for FPGAs. In particular, I'm going to make heavy use of higher-order functions, the capturing circuit, behavior, and layout. And recapturing layout is going to be a critical aspect is one of the important things about our approach, which makes it different from other approaches. We've done a lot of work with targeting Xilinx FPGAs. We now target Altera as well. And what we generate, we've got a flow where what we emit are things like edif, the umbrella of other hardware description languages, which the standard tools take and process further to produce the bit streams that you need to program these FPGAs. And we've got, the system we produce lives within the existing set of tools and environments for doing hardware design, so it plugs into existing flows for analysing and verifying circuits. And in particular, my colleagues at Chalmers have done lots of good work with formally analysing these descriptions. And at the end, I'll say a little bit about how we can take these same descriptions, which were originally done for FPGAs, and by changing the back end, generate code that actually runs on GPUs or runs as multi-threaded software on top of a kind of special kind of work stealing system that we developed at Microsoft. So that's the general plan. And as Simon said, feel free to ask questions as I go through, because I'm going to tell you too much information which you'll have no chance to understand in a 55-minute talk. So if there's anything particularly you want, we can zoom in on that, would be good. Otherwise, I'm going to hit you with lots of Haskell code, and I just want you to get an impression of what it's like to try and create an embedded domain-specific language for a particular application domain. And I can't expect to actually understand all the details. And I would very much like to show you that my collaborators are Mary Sheeran, who'll be along later on today from Chalmers, and Kuhn Klassen, who's sitting in the back row there. Well, then Mary is here. You made it. So how did I get into this line of work? Well, many years ago, I just couldn't understand why people were using these perverted descriptions for circuits with semicolons and all these things like them. It just seemed, why do we just use functions to model circuits? So I wanted to think of a circuit described by a pure function, which operates over streams of values. So the input, in your model for a circuit, you get the inputs to be just sequences of values, lists, and you can go to be possibly an infinite sequence, and this should be just functional, and the definition of a circuit, you should just take as input a whole bunch of streams, process them, and produce a stream as a result. And this thing here should be a pure functional description. And so I really felt there was some kind of synergy between trying to model digital synchronous circuits and calculations over streams. Just seemed like a natural thing. So here's an example of how you might describe a circuit, which has maybe got some feedback in it, so presumably there'll be a register somewhere, otherwise that loop might not be terribly well behaved. So what we wanted to do is to come up with a way of describing circuits and compose them together and layout, which just boiled down to a bunch of stream processes. And here's just a very simple example of a circuit. So this is how you can maybe implement it. So this is in Haskell, one model for that circuit. Loop, it takes circuit as one of its arguments. And the strange thing with this circuit is it's a higher order function. These circuit things take circuits as arguments, work on them, and give you new circuits back. And this circuit's got an A input, which you can maybe remember from the previous diagram here. And what it does is it runs this circuit with the A input plus this B thing here, which is the fed back wire, gets the result and returns it. So it seems like quite a straightforward kind of definition, but there's quite a few kind of subtleties here, including the high order function circuit. But look, this is B. It's on both sides of this equals. There's a B here, and there's a B here, and you're trying to define something. So this is a little bit mad, but this is what allows us to actually define the loop that we're trying to model. And because of the nice, lazy semantics that Haskell has, this is a perfectly valid program, and actually does it does the right thing. Why? Well, I can't in my 55 minute talk go into details for that, but I will execute the details for you. So here's a very, very simple example of a circuit that just keeps accumulating numbers. You get a stream of numbers in here, and it adds them with the previous sum, starting from the number 0. So it gets numbers in as an input stream and just adds them all up as it gets them. And you should be able to describe it by saying loop, adder, and after adder you have a delay. And what all delay does is it takes a stream and it sticks a 0 at the front. So this stream is like a delayed version of that stream. And I just want to model this just as functions over streams, functions over lists, and just run something under Haskell and have it do the right thing. So we can do that. We can do it right now. Because I typed it, during Simon's talk, I typed this into my Emacs buffer. Here's the definition of loop. You see at the top there. Loop takes a circuit, I have a parameter, input A, and then you see the description which ties loop. And then I put that circuit code, I call that, I use loop to call ACCore. ACCore is a description of what's in that picture you saw there. It took a bunch of A's and B's, zips, just lines all the A's and B's together, it adds them, and the delay is modeled by putting a 0 in front of it. And then I've got some sample input streams. I've got one here called I1, which has just got some numbers, and then I call ACC with I1 to get a result. So what does it do? Well, we can just load it up in the Haskell interpreter, what's it called? Accumulator. And you just ask it what R1 is, and it just gives you results. So just aim inside Haskell, just by typing a small amount of stuff, you've got the basics of doing circuit simulation and modeling of sequential circuits. But there's some kind of crazier aspects to this. I can define another input list, which is infinite. So this list, one dot dot, is an infinite list. It's 1, 2, 3, 4, 5, 6, forever. And so let's see what happens when we try and evaluate that. We'll get a result stream, and as before, we can call our accumulator, this time with I2. We'll load it up in the simulator, and I can take, this time we use a special Haskell function called take, which gives me just so many elements of list. So I'll take 10 elements of R2. Well, it's worked out 10 of them. I can take 20 of them. That's right. And the more I pull in this, the more I get. If I try and evaluate R2 itself, it just goes on forever. So we're able to describe a calculation that was infinite in some way, but we're able to just pull on just enough of it to get the result that we want. And the lazy evaluation of Haskell is a critical thing which helps us to work out. So with these small examples, this is going to give you some flavour, some inkling as to why I think circuits can model as functions and how that process, what that process might look like. So how can we model what FPGAs do? Well, FPGAs are built out of these lookup tables with 1, 2, 3, 4, and there are more inputs. And we can just use these higher order functions to model these lookup tables by giving them calculations as arguments. Then these lookup tables just exhaustively simulate them, work out the ones and zeros, and zap them into these basic lookup elements. And then we can layer a whole bunch of machinery on top of this to give us quite civilized looking hardware descriptions. And there's an example of a two-sorter. It's a circuit which takes two numbers and it sorts them so that one number is greater than the other number. You can imagine how it's built out of comparators, multiplexes, registers, and the way that you write these things in a domain-specific library kind of looks APL-ish. We define a whole bunch of combinators that have got left to right flow. We don't name the wires, and you can think of these descriptions somehow as being a textual representation of the picture. And furthermore, these descriptions not only tell you how things are wired up, they also tell you how things are laid out, which I think is a very important thing, especially for FPGAs, because you want to control your layout as well as how things are connected together if you want to get good performance utilization of your resources. Important combinators include one for serial composition, which takes two circuits, composes them together so the output of one circuit goes into the input of another circuit, and also they're laid out horizontally for left to right data flow. So this is something which takes two circuits as arguments, composes them together, and gives you a new circuit back. And this is a very powerful type of thinking, which just doesn't occur in normal hardware description languages. And behind this, there's a functional geometry scene where every gate initially has its own in its own geometry system, and then as you use these combinators, they all get superimposed and moved about, and you can get quite sophisticated layouts for using quite simple descriptions. And you can have you can also imagine combinators which go in different directions, right to left, up, down, etc. And it's completely wizardry. What you write is what you get. A lot of hardware tools work by you writing something which is kind of high-level-ish with some loops in it and case statements, and the tools kind of guess what you really wanted and try and give you that. Our system doesn't do any guessing. It just gives you exactly what you ask for. So if you want two things in different cells which don't share a register, you can get that. If you want to have two things squeezed in one cell, you can see that and you can get exactly that. So no synthesis, there's no guesswork or computation. This is just a framework to let you take an idea in your mind about the architecture of the circuit and get it into an FPGA. And you can also have four-sided tiles, and they're encoded in terms of two-sided tiles, and then you can make things like adders by defining one cell, and then you can have a column of so many of these, and to make the address, and they all work out nicely in FPGA. You get a nice column, or you can have a registered adder by superimposing a register over the adder elements, and you get a nice layer. So I'll give you my kind of standard kind of lab example, which is a sorting circuit. So it's which is based on Batch's algorithm for merging and sorting. And this is going to be a carefully laid out code. So on FPGA, we're going to implement a circuit which takes several of these streams of numbers, perhaps infinite streams of numbers, and it sorts them very, very quickly, perhaps in a pipeline fashion. And we're going to lay it out carefully so it goes really, really quick. Okay, so we're going to design a bunch of combinators to let us glue these basic blocks together to make the sorter work out very well. So our basic design approach is actually going to be bottom up. We start off basic elements, and we'll be introducing machinery to combine them to make more complicated things. And we're going to get layouts that are just absolutely super compact and with very high performance, but which are basically impossible to produce using the normal techniques. And I think the descriptions are beautiful, but that's very subjective. You might disagree. So this is a top-level view of what Batch's bipartite sorter looks like. We're going to design the circuit by working out how to do a merger circuit, and the merger circuit has to have as its input two inputs, each of which is sorted, and it's a bitonic sorter. So we need to have some extra properties, and the one that we're going to use is that one of the lists has to be in the opposite order from the other one. So this is in order 1, 2, 3, 4, 5, 6. This better be in order like something like 9, 5, 3, 1. Right, so just go in opposite directions. I'll show you a picture of that. And then these things are sorted themselves. And we want to use some recursive reasoning to work out how to implement this. Well, if you read some papers by Batcher, you can work out to implement this merger. There's a butterfly network that implements that merger. Then now we've never got to work out how to make a sorter, but we know how to make a sorter. Our previous picture showed us how to make a sorter. We make a sorter by making a merger and two sub-sorters. Here we get to the base case. This is a sorter with two things in it. How do we make the merger? Well, that's just the butterfly network, and we solve the bottom picture the same way. And this thing should sort, and you've got a little bit of reasoning. And you've seen a bit of informal reasoning about why it should be a sorter. Though if I just put this slide up first and try to convince the sorter, you might not believe it. You can describe the sorter using the normal technology. This is a VHDL. This is a part of a sorter description in a normal hard description language called VHDL. But it's just an absolutely bogging description. It has semicolons, and you can write all kinds of loops and accumulate values. What you write in no way seems to directly represent the circuits that you actually want to create. And really, I think this is a Soviet Union description that we have to get away from. And we should really be trying to think of these circuits as being like stream processes and glue them together, respecting wires and layout, rather than saying something slightly related and hoping some magical tool will turn this into the right thing, which always ends up in tears. So usually I have a board and this design and I run a simulator, but I'll just show you the screenshots to convince you that I have at some point I should run this circuit and go out to get some inputs and sort them. This is a a very widely used simulator called models. And when you run it, you get things like this sorter. I think this sorter's horrible because it just looks like somebody just thrown it, like got some pasta onto the FPG, and all the bits are in the wrong places. Your critical path is terrible. I don't want my sorter to look like. I want my sorter to look something like what I showed you on the previous slide, nice and nicer rectangle. And look at actual wires. That's a complete disaster as well. I think this is not a good circuit. So this is the two sort that I showed you before. We're going to use that as our basic element. And we would like it to be laid out like this, which is what's produced by the previous descriptions and combinators. And what we're going to do is we're going to introduce a whole bunch of extra combinators which glue these things together in interesting ways to finally get the sorted circuit. And one of the things we're going to use is a combinator called 2, which takes some circuit's argument, creates 2 instances of it, takes input and halves it, and sends the bottom half of input to one, and the top half of input to the other. They both then work in parallel, and then the outputs are then merged together again. So this combinator, again, is high order. It takes circuits as arguments, puts them together, and gives you a new circuit back. Again, this is the kind of thinking that's impossible to represent in languages like VHDL. We also have to talk about wiring, and in our system, wiring circuits are first-class citizens, which I think they deserve that promotion, whereas in other languages, the wires are somehow dealt differently from circuits, and that, I think, causes lots of problems. So there's somewhere in our network we need to do these things called riffles, where we take some bus, we break it, and we rearrange the wires in some way, and we flatten it again. So if I was good at a deck of cards, I could show you what a riffle was, but I'm not. And then an unriffle. When I used to use overhead projector slides, you could take this slide and do that with it to get this one. But I haven't quite worked out how to do it in PowerPoint. Well, I did actually, but I've already forgotten. So this is just like the opposite of that. And we're going to use another circuit called reverse, which is very easily defined in Haskell. This is called reverse. And these things you see at the bottom, that's the Haskell source code using a Lava DSL to implement all these pictures. Here's how you might define this 2 thing. 2 for some circuit R, any circuit R, that's that's got inputs out as the right shape. You define it by halving your input. You in parallel create 2 instances of R, and then you do another half. That's how you get a sorter. Here's another thing what we use. Something called evens. That's going to create many copies of some circuit F. It's going to take the input bus and break it into groups, adjacent groups of 2, and slap one of these F things across each one of these. In particular, we're going to slap 2 sorters across any adjacent pair of wires. So you get a picture like that. Interleave is another high order combinator that will take a circuit as a parameter and give a new circuit back. And what it does, it's a bit like 2, except it divides the inputs up in a different kind of way. So all the odd inputs go to the bottom and the even inputs go to the top, and then you undo that on the other end. So it's that kind of divide and conquer strategy. It lets you express the idea of, well, I've got this big problem, I'm going to break it down into 2 sub-problems, solve them in parallel, and compose a result. And I'm going to break my inputs in this way, and I'm going to merge the results of these in this other way to help me solve this big problem in terms of smaller problems. And then, once you've got that machine, you can start writing butterfly descriptions. Then you can almost read the butterfly papers and type in the descriptions. So you have these recursive circuit descriptions, which are unusual. You don't normally write recursive descriptions in all languages. So a butterfly of degree 1 of some circuit is just that circuit. A butterfly of higher degree you make by interleaving 2 smaller butterflies and then doing this evens thing at output. So that's how you make a merger. Here's the picture of a butterfly of degree 1. Here's a picture of butterfly degree 2, and you've got some interesting identities. Here's a butterfly of degree 3, and you can see that bigger butterflies are smaller butterflies. So this butterfly has got another butterfly in the top left-hand corner, and there's some identity. That's nice. And these things give you mergers, and you have to have its bitonic property. So these inputs are going in this order, these top inputs have to go in that order, and these input values they go through the network and they get merged. And you could write something like this in VHDL, but it really is, I think, absolutely awful and unacceptable. So then you can make the top level sorter of the basic mergers. So you want to have, you want to have a butterfly at the end, which does the final merge, and then you want to have use two subsorters to solve the subproblems, and then there's some wiring APL type machinery just to make sure that we observe the bitonic property. And that's what you do for a sorter of degree n. And for the base case sorter, you just end up with your comparator, your true sorter, because at that level you've just got two inputs and two outputs. So that's what you type. That's what you type in. I mean, I can show you what I type in. I have in my Emacs buffer. Haskell resort, and so this is the actual code that we type in, and these are the descriptions in Haskell that we compile to actually get to the sorters, and what comes out at the end are gates. And when you implement it on the FPGA, what you get a circuit like this. This is a sorter of degree 3, and it's a nice rectangular block. You can imagine inputs coming in here, doing all the FFT type interleaving and popping it there, and it's very compact. This one's complete pipeline. It's very efficient use of resources. There's a larger one. And these look like these pictures of FPGA circuits are unlike any normal FPGA circuit diagrams, because they don't have this kind of pasta thrown at the wall kind of layer, whereas these have these nice scrunched solid implementations on the FPGA. Now, if you took the layer information out, which I could do by just grapevine being the layer information, this is what you get. It's completely wrong. It looks like somebody shot a hole through the middle of it. And these circuits go a lot slower because there'll be some bad wiring here which ends up as being a critical path and it slows the whole thing down. It's not a very efficient use of resources either. And as an experiment, I made a special layout where I pushed the columns apart from each other so you can see the wiring between the columns, and as you can see, you get this nice FFT type wiring between columns. So the right thing is actually happening. The picture you had in your mind, the architecture you had in your mind, you were able to express it, both its layout and its behavioural connection, and get what was in your head implemented on the FPGA. And what you try and do is using normal tools, especially for circuits like this one, is not possible because the place tools put things, they use simulated annealing type algorithms, they put things at arbitrary places, and then they run out of space, or if they can place them, they can't route them. So this technique lets you do things which are impossible using normal techniques. Well, so by writing in VHDL,
you seem to have to map the logical description to the physical.
That's right. But the other techniques, what they don't do, because they don't specify the layout of these. They don't say where are all these gates. You have to run the placer. So what our system produces is. I mean, this is an example output from, but this is the netlist that we implement. And as you can see, we've got all the layout information attached to every single cell. We've computed that with functional geometry. There were no coordinates in what I wrote, but the generated system has got coordinates everywhere, all the time. Every cell has been placed automatically by the system. So the placer has to do nothing. We've placed it, then the router can work out the route. The normal technique, you have to run the placer, which is going to get, I think, a suboptimal placing. So either it's going to fail to place, or if it does place, it will find a placement that can't be routed when you're going above 90% utilization on your FPGA.
So the picture you showed that has the sort of the nice placement of blocks, that's only showing the CLD placement, right? Routing could go anywhere.
It could go all over the place, but it doesn't. So yeah, I don't have I probably have somewhere in my laptop a picture showing you how the routing works, but the routing actually is pretty much contained in that block. You get routing from one column to the next because of the nice variable. You don't get routing which goes out to the other corner of a chip and back. You get that kind of routing when you don't give the layer procedure. You get some pretty crazy routes or routes.
But you still have to define a placement algorithm.
And I described it in those pictures because those combinators I described told you how to put things together.
Yes, but this does not mean that it fits the physical structure of
the
it's one line, it might be a square.
Right, so I mean, if I define that one that was too wide to fit an FPGA, then I have no recourse to the law. I have to go back to my design and manually break it so that it goes over two columns, whatever. Because now it's your job to do the layer, because you've taken that job away from the automatic tool. And then you can look at. And normally when you FPGA design, you get a circuit layer that works and it's tiny, you freeze it, you don't ever do anything more to that circuit, and you ship it to the customer after you verifying it. But if your layer is deterministic, you can go, well, I'll explore some other approaches and change some combinators. So we find some other combinators, got different kinds of layers, and we're able to explore different kinds of sorters, different latencies and so on, and different degrees of performance, which I think we would not have done if you used normal. Would not have been easily achievable using normal techniques. So at Xilinx, this company that I used to work for, we solved lots of problems, real-world problems, which normal techniques were not able to solve satisfactorily. And our examples include things like filters, arithmetic circuits, sorters, FFTs, image processing circuits, things like JPEG 2000. So there are many examples where normal techniques just couldn't work. But our techniques were able to deliver a result that added to utilization or performance that was better than simulated annealing from VHDL or Verilog. So so looking at these descriptions, they look quite abstract. They just show you these boxes and how they're connected together. And I want to know, could I use the same descriptions but target different things? So we built two different backends. We built one backend which, instead of generating VHDL code, it generated code for a system at Microsoft called Accelerator, and we were then able to run these sorters on GPUs, and we were also able to generate C# code, which we're then able to run on a variety of threading platforms, some of which didn't work. The program didn't go faster, and some which did. There's a system that we worked on called CCR that was particularly effective at running these descriptions. So there's something going on with domain-specific language, with the use of the combinators and the way that described, which is capturing the essence of these parallel batcher sorts and merges, but not saying too much, so you still have the flexibility to compile to different types of targets. And we've also taken Lava type ideas and implemented in other languages. So we've got a version of Lava embedded in F#, so the butterfly thing you can describe in F# as well, though you can't as easily do the simulation. And then we've even embedded it in C#. So C# does let you, to some degree, pass calculations as arguments and get them as results. It doesn't look as pretty, but it's kind of possible. There's still lots of things that don't work out terribly nicely. So why did Lava work? Well, I think combinators were an important reason. These higher order functions for gluing things together and giving you new calculations. And these combinators give us powerful ways to compose things together. Also, circuits were represented as first-class citizens, so you could get circuits as arguments, do things to them, and return those results, which is a consequence of the way that we use the combinator. There's no accidental semicolons. There's no writing a loop and accumulating a value inside some process statement of HDL, which then has to be analysed and given to the VHDL synthesis tool, which does phenomenally complex analysis of it, builds control, data flow graph, and works out, you just meant a parallel instance of these gates. And I think we had we've used the power of abstraction. We've said what had to be said, and we've omitted what was not required, and the power over control of the layout. And it was using other techniques. It was just impossible to describe that. It's possible in VHDL to mark cells up with the layout using some kind of attribute, but when you compose things together, you end up writing basically systems of linear equations to describe layouts, and it's just not tractable. And then finally, my belief that functions actually more directly model circuits than imperative code written as sequential statements inside a process statement, which is analysed by a synthesis table. And another thing to benefit was that we embedded ourselves in an existing language. We didn't make a new language with new types, etc. We embedded ourselves in an existing language, Haskell, which happened to have enough power to capture the ideas that we wanted to talk in terms of. And there was a whole bunch of other benefits that we got by being embedded in an existing language, being able to do the simulation that I described, this whole bunch of other things as well. We could quick checks of our circuits. So it was good having an existing infrastructure to build on top of rather than creating a new language that required new tools. So in summary, I think Lava is an example of a successful application of functional programming for hardware design, because we're able to do things which were hard or impossible to do with other approaches, and we were able to capture some problem, I think, at the right level of abstraction and get good circuits out. We were able to solve real-world customer problems. There are a whole bunch of things with circuits. We created binaries. We shipped them to our customers. We got our customers to run them with arguments. They emitted VHDL, either Verilog. They didn't even know they were running a Haskell program. They were happy. They just produced the right circuits. And then finally, I think there really is something to the idea that domain-specific languages provide us with one useful weapon for being able to target many core systems. If we can capture problems in specific domains at a right level of abstraction, maybe we can then retarget them to things like GPUs and multivariate processors and FPGAs, and maybe we can think of doing instance languages as part of being some staged compilation system which successively refines your program from some high-level description all the way down to the details required to implement it on silicon or on GPUs. So that's my presentation, and I'm happy to take questions now. But I'm a bit ahead of schedule. So. I have more slides if you want them. But maybe I'll do that.
So what is the status of this work?
Well, so Lava is a bunch of Haskell libraries which you can download. There's a couple of versions of Lava. There was work that was done at Chalmers, and the work I did at Xilinx. You can download a version of Lava from a website, raintown.org/Lava, or from my Microsoft. Actually, go to my Microsoft website. There's a link to Lava. So there's some software that you can get now, and then there's recently that I've kind of ported to F# and to C#. It's something actively developed. It's not something It's not something I'm actively working on at the moment, but I hope to.
So I mean, a language like Haskell is a very good description language for what you're doing, but there are many things that you'd like to do in your simulator that you cannot really easily do in a functional language, which is, for example, adding a probe anywhere, stopping the simulation, investigating a state.
Yeah.
This is difficult to do in a functional language. That's my view. I don't know if you have.
Yeah, I would. The framework that we produced makes it hard, right? You give inputs and you see outputs, and you want to observe something intermediate. You have to do something to make that happen. But then we also do generate.
That's exactly because it's a pure functional language. That's the problem.
But we generate VHDL, we generate Verilog, so you could run the commercial. So something that the way that I run my script, really run the scripts, is I run them in Model Sim, in a commercial simulator. But the problem there could be, because we don't often do name wires, we don't, if you want to know something about an internal net, you then end up writing something that has to say, name this net blah, so you can recognize it in the simulator.
That's why I said it's a very good description. Language. You
So
might have, to make it really effective, you might have another underlying implementation that takes these descriptions and do all the other things.
And I think that's also maybe a negative aspect of being an embedded domain specific language, because there's some things that you would like to be tangible, which are not.
I didn't get the relationship between the picture you showed of why you were stopped at the airport and with the last part of the presentation here. What was the development board that you were using there? And I'm assuming you had some sort of input-output, and were you modeling that here?
Yeah, so I wrote a bit of a real wrapper. So what I described here doesn't show you show how the information comes onto the chip, gets attached to it. And, so I wrote some wrapper VHDL for that, and I'll probably even show it to you. And I wrote that in VHDL because for that kind of control-oriented circuit, there wasn't really any benefit in writing that in VHDL. Was that? So we could package. But I'm not entirely sure exactly what that is. But yeah, so there's a VHDL file that I wrote, which instantiates the circuit, gets inputs from some external entity. I typically use a JTAG chain to pump the values down, run them through the core, get the results, and then we so I don't run this from some kind of debugger. I integrate the logic analyzer, which I run on the PC. So I use Xilinx's chips code. So I blast the values down, execute them, get the results back. So that I didn't do in Lava. I wrote in VHDL. So I'm not saying that not all types of circuits are nicely described in VHDL. Particularly if you've got control-oriented circuits, then that's not so good. Data flow strings work quite well. For control-oriented circuits, we've explored the use of STRL, which is another kind of declarative language, and we've had quite a lot of luck with quite a lot of fun. Or I just write it in VHDL, because for some things, VHDL does give you the right instructions. Yes, sorry.
Have you looked at the combination of hardware and software, so hardware, software, code design? Is that something one could benefit from by having this descriptive language?
Yeah, so I mean, we thought about it, but I haven't done anything with it. I'm not sure if I really have a good answer for that. So it would be nice if you could write a Haskell program, part of which had some kernel computation, which did your FFT or whatever, and you could mark it up so that the compilation flow took the thing that was marked up as being a kind of lava block, implemented it on the FPGA, automatically created the infrastructure required to communicate between that FPGA over PCI Express, etc., with the rest of the Haskell program. So you can then marshal this data appropriately, pump it down, get the result, and get result back. So I wouldn't have to write this wrapper VHDL. So maybe there's some interesting work that could be done in that direction. Perhaps we've got some ideas, but we haven't actually done anything in that area. Well, if there's no more questions, thank you very much for your attention.